Managed to mess things up. That's just if anybody.
Thank you so much, Dr.
Good afternoon, everyone. Welcome to class. I'd like to begin with prayer. Is there a volunteer? Please.
Our dear Father in heaven, we are grateful to thee for this day, for the chance that we have to come here and learn and be able to develop. Father, we ask you for thy spirit that we can learn and understand the concepts that we're going to be learning, that we can be able to use them in the future. We love you so very much, Father, and we say these things in the name of Jesus Christ. Amen.
Amen. Thank you very much. All right, a couple housekeeping items. The exams, I think, are now back in the box with almost no exceptions at this point, except maybe one. The scores are entered into Learning Suite. I have also done a summary of points up till now and have created sort of a distribution curve to show effectively sort of your rank in class and kind of give you a ballpark estimate of where you stand in the class at this time. This is also in the content section of Learning Suite. So you might want to look at that. It might give you a better sense of how you are doing in the class as you approach the third and ultimately the fourth exam. I do have a review sheet here today, and if anybody would like a hard copy of that, please raise your hand, and we have one or two, three. I've also posted this on Learning Suite, and it should reflect accurately the distribution of questions on the exams. You will see, if you total things up, that there are more questions in total than questions on the exam, and that is because some questions have more than one part, and it includes things from different topics, so they are listed twice or so if need be. Okay. On exam 3, there is an issue with one of the questions. So they're in the long free response questions. I asked you to diagram the catalytic cycle for an enzyme in the glycolysis pathway. You are to pay attention to the enzyme specified. That is what I'm really looking for, is how that enzyme converts substrate to product. However, in the second sentence of that question, I mentioned substrate and product, and it's for the following step. So it could be very confusing, but I'm really just focused on the enzyme specified and not on the substrate and product that I mentioned. I'm one step off. Okay. I sent out an email about this, so if you need further clarification, please look at that. All right. Other questions, issues? We will then pick it up where we left off. We have been talking about this remarkable complex, the pyruvate dehydrogenase complex, which is a very large collection of enzymes that process pyruvate to acetyl-CoA. That is the intent, and this is what is accomplished by this complex. There are a series of 5 steps, and you should know what happens at each step of that complex. I'm going to move to slides now for a minute or two. And oops. Great. We have talked about step 1. This is where this cofactor, thiamine pyrophosphate, which is attached to E1, binds pyruvate. And that enzyme also catalyzes a decarboxylation. In step 2, there is a transfer of this 2-carbon remnant from TPP. Well, actually, initially, it binds, it attacks and binds to this flexible arm that has this disulfide ring structure. This is the lipoate, which is attached to a lysine on E2, this other enzyme that participates in the pyruvate dehydrogenase complex. So at this point, let me bring you into the picture. So at the end of step 2, we have coupled that 2-carbon fragment to the lipoate arm. As that species on TPP attacks the lipoate, it reduces the lipoate and is oxidized now from an aldehyde, formally, to a carboxylate. So we now have this thioester where we have acetate coupled to lipoate. Step 3 involves that flexible arm moving the acetate to a binding site on E2, on itself. So this extension that is on E2 has access to a catalytic site on itself where it transfers the acetate from lipoate, this flexible arm, to coenzyme A. Coenzyme A looks as follows. It's a very complicated molecule. You need not memorize its structure, how to draw it, but notice that there is a thiol group at the end. And this is the part that interacts with the acetate. So we're transferring the acetate from one sulfur on lipoate to a sulfur on coenzyme A. This produces acetyl-CoA, this very big molecule that's going to carry the acetate onto the citric acid cycle. So this is step 3. In step 4, we have an issue. The issue is that we have produced the desired product, but we have left the lipoate in this reduced state. And in the reduced state, it is not catalytically active, and consequently could not undergo another round of catalysis unless we were able to reoxidize the lipoate, reform that ring, and allow it then to interact with the 2-carbon fragment that comes from pyruvate. To do that, there is on E3, okay, so this is the third enzyme in that complex, an embedded FAD molecule. FAD is this electron acceptor donator. Let's see if I can find it. I think I have a picture of it. But FAD is actually deeply embedded in the E3. It does not have the ability to exit and re-enter. Once it's in place, while it can undergo oxidation and reduction, it cannot leave and carry electrons away. But it does access the lipoid arm. So the lipoid arm, which is attached to E2, this long extension, comes over and touches E3, where those electrons are removed from the lipoid, reoxidizing, reforming the ring, and FAD is reduced to FADH2. This is step 4. So at the end of step 4, we will have the ring reestablished. The FAD will be reduced, but we now need to remove those electrons from FADH2, reoxidize it so that it can participate in another round of catalysis. And this is accomplished by NAD plus coming in. There is a binding site on E3 that adjoins the FADH2 location. And those electrons are transferred now from FADH2 to NAD plus. We form NADH, which now can move away from the E3 enzyme. It leaves the FADH2 as FAD in its reoxidized state, and we are now ready again to carry out another round of catalysis. So this is a very elaborate process involving many copies of E1, E2, E3. It has these remarkable cofactors, and this lipoid arm is able to access sites on E1, on E2, and the FAD on E3 to be reoxidized. In total, there are 3 oxidation reductions. So as we move the 2-carbon remnant from TPP to lipoid, that is an oxidation. The ring is reduced. The aldehyde is oxidized to acetate. There is the step 4, where FAD is reduced to FADH2, and the ring is reoxidized. And then finally, the third oxidation reduction is the reoxidation of FADH2 to FAD with the reduction of NAD plus to NADH. Okay, are there questions about this? We will talk about regulation a little bit later. There are this process is regulated. We'll see that most of the regulation makes sense. That is to say, for example, if you have abundant acetyl-CoA, that tends to inhibit the pyruvate dehydrogenase complex. Yes?
Once it's active, FAD is supposed to have a plus side and positive side.
No. No, it doesn't. Okay, other questions? So for FAD, the way it's considered is that there are 2 hydrogens transferred, each with 1 electron. So there is no plus. How it happens stage-wise is maybe a little bit. Okay, this concludes then our discussion for the pyruvate dehydrogenase complex. And we're now going to move on to talking about the citric acid cycle. Oops. Are you seeing this on your screens? Okay. The citric acid cycle is also called the Krebs cycle. It is also called the tricarboxylic acid cycle. It is a series of 8 steps, 4 of which are oxidation reduction reactions. So in the end, that 2-carbon piece that comes in as acetate is oxidized, and there is no accumulation of the intermediates in this cycle. That is to say, we lose 2 carbons as carbon dioxide, one at step 4, one at step 3. These are oxidative decarboxylations. We'll produce, 3 of those oxidations produce NADH. One of them produces an FADH2. There is also a GTP, which is energetically equivalent to ATP, produced in step 5. So this is this energy hub inside the mitochondrial matrix. We're carrying out these oxidations, which is going to release energy as electrochemical energy to these reduced molecules, NADH and FADH2. Those will carry electrons to the electron transport chain. The energy then will be used to generate ultimately ATP. So we are really in the process now of capturing energy in the form ultimately of ATP. Some of this remains as NADH or FADH2. But so there are these 8 steps. The book describes step 1 in a fair amount of detail. Steps 2, 3, 4, and 5 are also described briefly in the text, and steps 6, 7, and 8 are barely touched on in the text. I would like you to know these reactions at the level described in the text. Okay, so just give you a heads up. Will there be electron pushing, drawing out of mechanisms? The answer is no. However, you should know the sequence in which events happen if they are described in the book. Okay, so just give you a sense of what to take away from this. Okay, let's consider step number 1, the citrate synthase reaction. We take that acetate, which is coupled to coenzyme A, and in effect, we're going to transfer it to a copy of oxaloacetate to produce citrate. Citrate has 3 carboxyl groups and it has a hydroxyl on it, 6 carbons now. It is a very negatively charged species. The citrate synthase is going to then bind both the acetyl-CoA and it's going to bind the oxaloacetate, but it has an ordered processing. It binds oxaloacetate first. And with binding, the sense is that it opens up now a binding site for the acetyl-CoA. It's going to position the acetate right next to the oxaloacetate to allow for the reaction to take place. So, unlike hexokinase where either substrate can bind first, In this case, we have an ordered process. Oxaloacetate must bind first to allow for the acetyl-CoA to bind. It is necessary that we have oxaloacetate to allow this enzyme to function. And this poses a problem. If we are using oxaloacetate for gluconeogenesis, we have to be careful. If we remove all of the oxaloacetate for gluconeogenesis, let's say, then we cannot run the citric acid cycle. It ceases to function. This can be a problem if you are relying on fat as your sole source of energy. So a rapid change from a mixed diet to a lipid diet can lead to the inactivation of the citric acid cycle and all of the downstream ramifications of that. All right, I'm going to come out here and I'm going to I want to come back and I want to outline this reaction for you. Okay, so you won't need to do this. You won't need to draw this out on the exam. Nevertheless, I would like you to have a sense of what is going on. So this is our oxaloacetate. It binds first. It leads to a conformational change that now allows for the positioning of the acetyl-CoA, this very large molecule, next to it. Okay, so this hydrogen is somewhat acidic. It is alpha to a carbonyl. It is proposed, I don't know that it's proven, that there is an aspartate that neighbors, that's part of the active site that is neighboring this acetate group that is going to remove this proton. This pair of electrons then will move in and attack the carbonyl carbon. This will push a pair of electrons out. And there is proposed a histidine that is next to the carbonyl that will donate a proton to form a hydroxyl group. Okay? Now, in the book, it shows this pair of electrons going up here, and this pulling off a proton, and then coming all the way back down and producing the carbanion again. That may happen. There may be delocalization of that electron over multiple nuclei as part of this process. But to begin with, and in the end, you end up with a carbanion here, which attacks the carbonyl carbon, and this produces now, here, let me get this right, redraw this, this produces now an intermediate which is citroyl-CoA, okay? So we actually have this 6-carbon tricarboxylic acid attached to coenzyme A initially. This process of coupling leads to, while we're having access to this site, this thioester bond is a very reactive species comparatively. It's easily hydrolyzed. The citrate then comes off. The coenzyme A then comes off, and there is a reprocessing of the coenzyme A through the pyruvate dehydrogenase complex to pick up another acetate. Okay, So this is step one. Let's move on to step two. This step involves an isomerization, a rearrangement of our citrate to a molecule called isocitrate, which differs in the location of the hydroxyl group relative to the rest of the molecule. It does this through removal of a water to form a double bond and an intermediate called a conatate. A conatate then is where the name aconitase comes from. After this water is removed, it is reinserted into that double bond, but from the opposing side, if you will, coupling now coupling the hydroxide to the adjoining, to a carbon one, to the adjoining carbon. So let me just highlight this a little bit. So this hydroxyl group is going to be moved, producing this intermediate, and then reinserted on the opposite, a carbon, one carbon away from its original location. This enzyme is going to introduce us to what is termed an iron sulfur cluster. This feature of the aconitase enzyme is not unique to it, but it is the first time that we have seen this iron sulfur cluster. We will see it again with other elements of the electron transport chain, but this is the first time we've seen it. Okay, let me just kind of walk you through what's going to happen. So this iron here, so notice that there are 4 irons, 4 sulfurs. Some of these sulfurs are from the enzyme, represent cysteine sulfhydryl groups that have been coupled or converted into sulfides and coupled to irons. And there are all other sulfurs that come from the solution or from enzymes inserting them to form the cluster. But this one iron up here in the corner is going to participate in the reaction. The reaction gets started by a base, and this is potentially a serine. Okay, remember chymotrypsin and the activation of the serine? There are mechanisms proposed for this that involve the activation of the serine with abstraction of this proton right here. This pushes the electrons here to form a double bond, and this hydroxyl group will come off and be bound to the iron. So the iron has these open d orbitals, these coordination sites, and that pair of electrons on the oxygen, the OH minus group, are nicely accommodated on the iron. This is where things get a little crazy, because in order to form isocitrate, we need to effectively invert the intermediate. Some propose that this is a little bit like flipping a pancake, that the intermediate gets inverted, actually gets turned 180 degrees within the active site. That potentially could happen, but it seems strange to me. Anyway, that is one proposal. Another possibility is there is a conformational change such that the position of the intermediate is such that this hydroxyl now that is residing on the iron is going to be added to this carbon as it comes back off. There's a double bond here. This will swing out and pick up a proton, presumably from the same base that, or the serine potentially, that pulled it off. You don't need to know the details of the electron pushing, but you should know that you form this double bonded species, this aconitate, that's accomplished by proton abstraction and a hydroxyl group being moved to the iron and then reinserted to to the double bond, but on the adjoining carbon. Okay. Step 3 is our first oxidation reduction reaction. This is going to convert isocitrate, a 6-carbon tricarboxylic acid, into a 5-carbon dicarboxylic acid. This is a oxidative decarboxylation reaction. Okay, so let's consider this. I think I will use the board here for just a second, kind of walk you through this. If I can remember where everything goes. Okay. This is the isocitrate part of things. We've got too many hydrogens. Okay, so to begin with, we're going to carry out the oxidation part of things. So what we're going to do is we're going to have a base out here that is going to take off this proton. It's going to lead to the formation of a ketone. And this hydrogen is going to leave as a hydride. Okay, so a 2-electron transfer from the isocitrate to this NAD plus to form NADH. This represents the oxidation reduction step. The hydroxyl group has been oxidized, the NAD plus reduced. So let me now redraw this after this initial reaction. We have this all right, just drawing these out. In the next step, there is going to be a decarboxylation, and this group on the side here is going to get this. We're going to swing and move this down here, and I'm not doing this right. Okay. Sorry. We better stick with the slides. We're going to get an intermediate So we see here the oxidation has taken place. So this is the proton that gets removed. The hydride comes off, binds to NAD+, and we end up with this species. Now, this is the decarboxylation step. We move electron density out onto this oxygen. Now, you'll notice that there is a very unusual ion that stabilizes this intermediate. It's not a magnesium, it is a manganese ion that is stabilizing this. So very unusual, and it allows for this to be stable. So we end up with O minus here and an O minus here, both of which then are counterbalanced by this +2 charge on the manganese. These electrons then reform the carbonyl. This electron pushes out, picks up a proton from the enzyme or from the solution. It's not known. And this leaves us now with this new molecule, 5 carbons long. It is an alpha keto acid. So that means that we have alpha to our carbonyl. We have this ketone group. This is a dicarboxylic acid. It is called alpha keto glutarate. In the next step, we're going to undergo a second oxidative decarboxylation. So in step 4, we're going to have our second redox reaction. We're going to produce another copy of NADH, and we are going to lose one of these carboxyl groups. In fact, we're going to lose this one right here. And this keto group is going to be oxidized to a carboxylate, and it's going to be coupled to coenzyme A. So let me just show you, outline this. So the alpha ketoglutarate then is decarboxylated. This keto group over here of the alpha keto group is going to be oxidized to a carboxylate and coupled to coenzyme A. This now is this four carbon dicarboxylic acid is called succinate, but it is coupled to coenzyme A and is called then succinyl-CoA. This process involves a complex that is almost identical to the pyruvate dehydrogenase complex. It is this large collection of E1, E2, E3 enzymes. It uses TPP coupled to E1. It uses lipoate coupled to E2. E3 is identical to the E3 found in the pyruvate dehydrogenase complex. It differs in its specificity. So this complex will only bind alpha ketoglutarate and not pyruvate. And the pyruvate dehydrogenase complex will not bind alpha ketoglutarate. Likewise, so here's the keto species that binds to TPP. Okay, remember pyruvate, we have a 3-carbon species that was bound through the carbonyl to TPP. Then there was a decarboxylation. This CO2 minus here is going to come off, forming a carbanion on this carbonyl, which is going to attack the lipoate arm, reducing it, oxidizing the keto species to a carboxylate. Then the lipoate is going to move that 4-carbon species the succinate over to a binding site on itself, on E2, where you have coenzyme A, and transfer them from the succinate from the lipoate arm to the coenzyme A. It comes off, then there's the reoxidation of the lipoate arm on E3, and by reducing initially FAD to FADH2, that gets reoxidized as you reduce a copy of NAD plus to NADH. Here we have then the products of this are NADH. We lose a carbonyl as carbon dioxide. We couple the product to coenzyme A, this succinyl-CoA. All right. So this complex is very analogous to the pyruvate dehydrogenase complex. It involves the same 5 steps that we reviewed for the pyruvate dehydrogenase complex, but it uses this 5-carbon species, alpha-ketoglutarate, rather than pyruvate. Okay, questions? We've gone through a lot of stuff pretty quickly. Yes?
We have never removed all the carbons that were once part of glucose, right?
If I understand the question, we have a 2-carbon piece that is a remnant of glucose. It comes in as acetate, as part of acetyl-CoA. Okay, that is a remnant from glucose. In these 8 steps of the citric acid cycle, we do lose 2 carbons as carbon dioxide, but they are not those 2 carbons that come from acetate. Not on this, I mean, eventually they become part of the CO2s that are lost, but not to begin with, okay? I don't think I'm answering that very well, but the acetate is not, doesn't represent the 2 carbons that are lost during the citric acid cycle as part of the initial cycle, okay? Yes?
So on this slide, the alpha-ketoglutarate has, on the previous slide, there's a carboxyl group per carbon. Yeah. So the C1, the O is a carbon, and you slide forward, and it goes to
it's just the way it's oriented. It's the exact same molecule. All right, let's talk about step 5 for just a minute. This is the succinyl-CoA synthetase reaction. This is where we're going to generate GTP. We're not undergoing an oxidation or reduction here, but we are nevertheless generating a high energy molecule, GTP, which is energetically equivalent to ATP. So, and this happens through 3 steps, which are kind of interesting steps. Let me indicate that these thioester bonds are high energy bonds. They preferentially separate, leaving the coenzyme A. It's sufficiently energetic that we can actually couple inorganic phosphate, which is not particularly reactive at all, to that carboxylate to form a phosphoester. Okay, so let's just look at this. So the step 1 here, we bring in our succinyl-CoA, and it is this feature here. This can be thought of as a good leaving group if you're talking organic chemistry. Phosphate is sufficiently, this is highly reactive, allowing a relatively unreactive species, phosphate, to displace it. And so we form briefly then this phosphosuccinate species at the active site of the enzyme. The active site has a histidine present, and this phosphoester is still in a energetically, in a high energy state, which allows then the histidine with a pair of electrons to displace the phosphate. That means a couple to the phosphate, releasing succinate, which is the product of this, and leaving the histidine phosphorylated. Then a GTP comes in, is going to pick up the phosphate from the histidine, forming GTP, and placing the histidine back into its original state. Okay, so a series of reactions then. The coenzyme A, the leading group, allows the phosphate to couple to the carboxyl of the succinate. Then the phosphate becomes a good leading group. The histidine at the active site is able to displace the succinate, coupling the phosphate to the active site histidine. Then GDP is able to come in and displace the histidine, pick up the phosphate, forming GTP. Okay, so that's the level you should know this. I won't be drawing this out on the exam, but you should know the steps involved. All right, we'll stop here. We'll come back and touch on the last three steps in the last four steps, three steps in the citric acid cycle. We'll talk a little bit about regulation next time, and then move on. I'm going to share an experience. I don't think I've actually ever shared this one before, but I had occasion to think of this recently, and I thought it was, it elicited a lot of memories. When I was in graduate school, I was in New Haven, Connecticut, and I attended church with a family who were longtime residents of Connecticut. They didn't live right in New Haven, they lived a ways out. They were an interesting couple, the parents. They were both chemists, and I think because of my being a chem major, chem grad student, and their being chemists, there was a kind of affinity, or at least they felt sorry for me. And they would invite me to dinner frequently. And I got to know their family. I mean, I was there for 5 years. I got to know this family really quite well. They had several children, but one of their younger children was a young woman by the name of Heather. I think she was probably high school age, junior high, high school age during the time that I got to know the family. And I didn't, you know, once I graduated, I moved away from Connecticut, moved to Massachusetts, and I lost track of this family. Their names were Hunters, Byron and Peg Hunter. And I really hadn't thought much about them, but one day, out of the blue, I was actually here on BYU campus. Not as I still lived in Massachusetts, but I was doing research with a colleague who was in the Department of Chemistry. A long story, but we were going to lunch, and I happened to see Byron Hunter, and we had this wonderful conversation where we sort of caught up on all of the events that had transpired in the prior 15 years or so that had passed. But as part of that conversation, I found out that Heather, this younger daughter, had married, had 3 children, but was now dying of cancer. She had had this cancer, breast cancer, She had been struggling with it 5 years. It was metastatic. It was now in her bones, in her brain. She was really in the last stages of her life. Her father gave me her phone number, and I called Heather and on more than one occasion, and we had rather long discussions about her life, her feelings, her frustrations, and the effects of the disease. She was deeply concerned about her kids. They were still quite young, and she was reading books and recording them. She was recording messages for them to be played on their 12th birthday and 15th, 16th birthday, and so on and so forth, in an effort to try to be there for them. I have to say that this was very trying. Well, it was horrible for her. It was distressing beyond words. She was in pain. The disease was disfiguring, debilitating, and in the end, it did take her life a few months later. But during that time, I became, I don't know, I guess it caused me to wonder why her prayers and her family's prayers were seemingly going unheard and not being answered. And I started praying about this. I don't know that I was particularly polite about it. I was asking in a very sort of aggressive way why this was happening to her and why weren't her prayers being answered. And after weeks of praying about this, I got an answer. And the answer went something like this. Stephen, I'm aware of Heather. She is not being left alone. I'm completely aware of her situation and all that she's going through. It is not a matter of my not loving her. The issue is that she is being prepared for a great work, and there is no other way in which she can be prepared. This event, I think, has changed my perspective a great deal about different situations for different people. I understand that we live in a fallen world with imperfect bodies, and we are subject to disease. We are subject to breakdown of tissues and, bad biochemistry left and right. But sometimes our problems are preparing us for things that we cannot yet understand and comprehend. Truly, our Savior could not have accomplished all that he needed to had he not gone through what he did. I am so grateful that he was willing to pay those ultimate prices again and again and again to allow for our being blessed eternally. Anyway, Heather, I believe, has gone on to do something, is part of something great in eternal. And there was no other way for her to accomplish that without that preparation. Anyway, something to think about. Thank you very much. Thank you for indulging me.